Section 1.2, finding limits graphically and numerically. Um, let me tell you that when you're looking for the limit of a function, you are simply trying to find the y value of that function as the x values approach a certain number that we'll call c. So as x gets close to c, what happens to the function values? Typically, and for the most part, you will be able to find limits of most functions by simply plugging in the value of x into the function by what I call just a straightforward evaluation. However, in some cases, finding the limit will be a challenge. So we'll consider evaluating limits in a straightforward manner. Let me just give you a few of them right here. So say, for example, if you're looking for the limit as x approaches 0 of, let's say, 5 over x minus 1. Notice that when you plug in x equals 0, we have 5 over negative 1, and that's just negative 5. So you're able to plug in the value of x as x gets close to 0. What this says is, as x is close to 0, what happens to 5 over x minus 1? What number does it approach, if it even approaches a number? If it doesn't approach a number, then we say that the limit exists without bound. That is, it just keeps on increasing or it keeps on decreasing. Sometimes the function may oscillate between two values. And then for another case is that as x approaches one value, the function value may be two different values at the same time. So we'll look at that possibility as well. Another example, find the limit as x, here let's say approaches 1 of x minus 1 all over x squared minus 1. Now notice here when you plug in x equal to 1, we get 0 divided by 0. We call this an indeterminate form. We'll talk more about this when we get to that particular section. But this is called an indeterminate form. There are other indeterminate forms out there. You can have infinity divided by infinity. You can have 0 raised to the 0 power. You can have infinity raised to the infinite power. 1 raised to the infinite power. And then it can be negative infinity divided by negative infinity. And not necessarily in that order, because it can be positive infinity divided by negative infinity, or negative infinity divided by positive infinity. And the list actually goes on and on. If the function is said to be an indeterminate form, then we can do one of three things. And again, we have sections for this that we will discuss it later, but just want to give you an idea and not to limit ourselves just to this one particular section. So here, if a function is in an indeterminate form, then there are one of three ways to determine the nature of the limit, namely one, you can factor, two, if there's a radical, you can try to rationalize, and three, something that we won't get to until calculus 2, but it's called L'Hopital's rule. So I want to give you a complete statement here. In this course, I will consider factoring if possible, or rationalizing if possible. In the particular case where you have here an indeterminate form. So for this particular example, the denominator can be factored. So we're going to factor that. So this is the limit as x approaches 1. This is x minus 1. And then down below we have x minus 1 times x plus 1. But notice that you can cancel out the x minus 1. And so that leaves us then the limit as x approaches 1. And up top we have 1 divided by x plus 1. Now see if you can plug in x equal to 1 for x in the function. And we can do that, and we do not get discontinuity or something that's undefined. So we get just simply 1 over 2. Notice that we had a discontinuity at x equal to 1, but we removed it. So we call this a removable. I don't know why it wants to go thick on me. Okay, a discontinuity that is said to be removable. So now, in looking at this section, finding limits graphically and numerically, there's some common types of behavior associated with non-existence of a limit. Three possibilities here is that first, the function approaches different values from the right side and the left side as x approaches some value c. And then secondly, f of x increases or decreases without bound as x approaches a common number c. And then thirdly, the function is said to oscillate between two fixed values as x approaches some fixed value of c. Well, the first possibility is that show that the limit here, the absolute value of x divided by x, does not exist. And we'll see that it does not exist because something happens to the absolute value of x depending on the value of x itself. So here, definition for the absolute value of x, we say that it's equal to x if the x values are positive or 0. And we get negative x if x is less than 0. So the two natures of the absolute value of x comes into play here. So we look at as x approaches 0 from here, the right side. And that's what we're doing over here as x approaches 0 from the right. As x approaches 0, say plus sign for the right. So the limit of the absolute value of x over x as x approaches 0. Here we say from the right, we drop the absolute value sign. So we get the limit as x approaches 0 from the right of x divided by x. And that gives us x divided by x is just 1. And the limit of a constant, we'll find that out, will always be a constant. So here we get 1. It's a really bad limit. We erase so much. So as x approaches 0 from the right side, the values for x are positive, so we get just x divided by x. But then as x approaches 0 from the left side, we have to use the second part of the definition for the absolute value. So you look at that, we have the limit as x approaches 0 from the left here of the absolute value of x divided by x. Well, we drop the absolute value sign, but we negate that negative as well. So this is the limit as x approaches 0 from the left, and this becomes negative x divided by x. We get negative 1. So since the left-sided limit does not equal the right-sided limit, the limit at of f of x as x approaches 0 does not exist. You would expect some type of discontinuity because we have this x by itself in our denominator, and as x goes to 0, well, quite naturally you get division by 0, so you know that's not allowed. But we do the analysis of it, and indeed the limit does not exist because the limits from the left and the right side do not agree. Secondly, discuss the continuity or the existence of the limit 1 over x squared. Notice that this particular function is always positive. Because of the nature of the x squared. When you have 1 over x squared as x approaches 0, well, you know that 1 over 0 squared is not defined. Going back to pre-calculus algebra, you remember that x equal to 0 for this particular function is said to be a vertical asymptote. That's better. The graph is always positive. Recall f of x equals to 1 over x. This was our basic rational function. And for that particular graph, we said that the vertical asymptote was x equal to 0, and the horizontal asymptote, you recall, is y equals 0. And so for this one, for the basic function, when x travels from the left it wants to cross the isotopes, but it can't. And this function, when x is, don't want to write it there. When x is less than 0, the function is negative, and when x is greater than 0, the function is positive. For this basic 1 over x squared. So you recall that we had something like this, something like that. And if you take the algebra and apply the calculus, the limit of 1 over x as x approaches 0 from the left side, look, as x goes to 0 from the left, this goes to negative infinity. And then the limit of 1 over x as x goes to 0 from the right side, as x goes to 0 from the right, this guy blows up, right, to positive infinity as x goes to 0 from the right. As x goes to 0 from the left, it blows up down in the abyss, and that's why we get the negative infinity. So this is positive infinity. Now obviously, if the limit is infinity, we say that the limit does not exist, because infinity is not a number that man knows. So now coming back to this particular function here, as when x is less than 0, the function is positive. When x is greater than 0, the function is positive. The vertical isotope is x equal to 0. The horizontal isotope, y equal to 0. And so the graph that we get here, the function is always positive, so that means it's always above the y-axis, right? And as x approaches 0 from the left, we get positive infinity. As x approaches 0 from the right, still blows up to positive infinity. Okay. So we say that the limit does not exist. Here it is set to extend without bound in the positive direction. Now we can take that same problem and apply here another example. The limit as x approaches 0 of negative 1 over x squared. Just flips this graph. Instead of going upstairs, it goes downstairs to Hades. So the limit here does not exist. If infinity existed, this guy would obviously give us negative infinity. If infinity existed as a number, I mean, infinity does exist, but we can't really claim to just one number because it keeps on changing. When you get to infinity, you always get +1 on that, and then you keep adding, and so we can never get a clear grip of it. So that this example here gives the support for the function increases or decreases without bound as x approaches some value c. Then thirdly, discuss the existence of the limit of sine 1 over x. Sine 1 over x by the graph, it will oscillate heavenly between -1 and 1. So we say that -1 is less than or equal to sine of 1 over x, which is less than or equal to +1. So because of the oscillation, you cannot pinpoint that the limit as x approaches 0 for this particular function. You cannot pinpoint that it's either this number. It has to be this number. It can't be, oh, it's -1. Oh, no, it's +1. Is it -1? Okay, yes, it is. But no, it's +1. It keeps on going back and forth. I mean, it oscillates in a chaotic motion. And so because of that, the limit does not exist. Okay. Next, we will discuss the limit in the form of its strict definition of epsilon and delta.